Swayam Prabha. Digital India. Educated India.
Alright, so welcome to the next class. So last time we essentially ended the topic of thermodynamics with what we called the third law of thermodynamics, third law of thermodynamics. And towards the end we saw that why we really need a new theory to understand systems, physical behavior of systems, especially at temperature very close to 0, right. And essentially what we saw in third law was there were like a few formulations, right. So according to Nernst's formulation, we saw that as limit of temperature goes to 0, the processes the processes happen without any change in entropy, right. So as you take temperature to very close to 0, the entropy difference between initial state and final state is very tiny, right. So in the second statement, which we defined as Planck's statement, we even saw that not only the differences in entropy, not only the entropy change, even the absolute entropy as temperature goes to 0 becomes 0, right. So it's like the system has absolutely no disorder in its structure, right. And moreover, we also basically proved a statement which is unattainability of t equal to 0, right. So unattainability of t equal to 0 state, right. And we saw that due to consequence of the absolute entropy value going to 0 as temperature goes to 0, we saw that there is no way we can achieve t equal to 0 state in finite number of adiabatic and isothermal steps, right. So basically we saw it is impossible to achieve t equal to 0 state in finite number of steps, right, steps. And we also looked at a few consequences of third law, right. So basically the few consequences and some of the important ones being the expensivity of any solid, right. So expensivity of solids, which we usually denote by beta at constant pressure, that goes to 0, right. It means that solids do not really expand as you heat them up while they are at temperature equal to 0, right. Also we saw that the heat capacities Cp and Cv both go to 0 as temperature goes to 0, which implies there is zero heat is required to warm systems or materials which are at absolute t equal to 0 temperature, right. So there is no heat required to increase their temperature. And also we saw that the Carnot efficiency, right, eta, which we saw that it is 1 minus TL by TH. Now if we somehow create a reservoir which is at absolute 0 temperature, right, becomes, so eta becomes 1 as TL becomes 0, right, which means the entire conversion of heat into work is possible, and that goes against the second law of thermodynamics, right. So basically the take home message was like it often becomes very difficult to comprehend the physical properties of systems as temperature approaches 0, right. And therefore, we really need a much more sophisticated theory to understand the behavior, physical behavior of systems operating near the temperatures which is absolute 0, right. And that is exactly what we will start in today's class, right. So, we will start a new topic which is the statistical physics, right. Okay, so, basically we will start with statistical physics. Okay, so statistical physics, and essentially this is the theory developed to study the properties of large group of particles which are either interacting or non-interacting, right. So, basically, so a theory developed. So, this is a theory developed to study the properties of large group of particles, right, both interacting and non-interacting. And our approach basically will be to use the concepts of probability theory and statistics to solve physical problems dealing with large collection of particles, right. So, basically, so you use concepts of probability theory and statistics to solve physical problems for large n systems. Okay, so, this is important. So, this theory works only if the number of individual constituents of that particular system is very large, right. So, if we have handful of molecules or atoms like 10, 15 or something, this theory does not work, right. So, it works only when n really goes to a very large number, and that we will essentially see why that condition is possible, is required, all right. Okay. So, and our approach basically will be through the concept of entropy, right. So, remember when we discovered the new concept of entropy through the Carnot engine, which is like Q by T as a new conserved quantity, we basically touched upon little bit of statistical physics, and we made sense of the physical meaning of this entropy as log of number of individual microstates in the system, right. And our approach will essentially be the same, right. So, we will basically calculate the entropy of a system and we will maximize it, right. And the maximize entropy according to second law is indeed the equilibrium state of the system, all right. So, basically, but we have to fix one small fundamental, basically fundamental problem that we encountered when we discussed about statistical meaning of entropy, right. So, essentially what I am saying is that so from thermodynamics, so we defined entropy, we called it S as the ratio of heat exchange happening at a particular temperature, right. So, Q divided by T, and this was important because this was a magical quantity in some sense, which came out to be another conserved quantity in the Carnot engine problem, right. So, we knew that as we undergo a cyclic process and come back to the initial point, the total internal energy of the system remains conserved, but we also saw that in a reversible Carnot engine, the Q divided by T quantity is also conserved, right. And later on we also saw that from statistical point of view, right. So, statistical definition of entropy goes like this. So, we saw that entropy is nothing but Boltzmann constant times log of omega, where omega is number of accessible microstates, right, in a particular macrostate, right. So, this is how we defined this entropy. And we also saw that the microstates basically represent the position or the coordinates of any particle, any system in a in a position and momentum space, right. So, we saw that microstates are essentially Ri and Pi coordinates of all the molecules in the system, where I runs from 1 to so on up to 10 is to the power 23, right. And corresponding to every single microstate there is a macrostate, right. And we also saw that a macrostate can have multiple microstates, right. So, a single macrostate might be associated with huge number of microstates, and we defined that as the multiplicity of a particular microstate. But the problem that I'm basically talking about is the following, right. So, remember, since we are defining microstates as the position and momentum coordinate of our of molecules of our system, and since both momentum and position coordinates are real numbers, right, and they can range from, so basically what I am saying is r, which is typically x, y, z positions of a particle in a real space, and similarly p is px, py, pz, right. And what I am saying is, so this x is a real number, right, real number. So, therefore, when we say that x x belongs to x lies between a range of 0 to say some x prime, right. So, there are, so on a one dimensional axis, so this is 0, this is x prime. So, there are infinite number of real numbers, right, infinite real numbers, right, and same is true with y, same is true with z, and so on with px, py and pz. So, what I am saying is that you can always divide your real space into infinite number of more real numbers, right, in which case your number of microstates will tend to infinity, right. So, we are and we do not really want that to happen, right. So, our entropy can't really diverge, it cannot really be infinity, it is a finite quantity which we can measure as heat, right. So, how do we get out of that problem, okay. So, so therefore, we will move into the concept of phase space and discretization of phase space, right. So, phase space. So, let us first define what is phase space, okay. So, phase space is essentially a plane in the position and momentum coordinate of a particle, right. So, say this is p and this is r, right, and for one particle, that particle will be evolving as a function of time, colliding with other particles of the system, other molecules of the system. It will be exchanging its position, its momenta all the time, and it will trace out a certain trajectory in a plane of p and r, right. So, basically this p r plane of a plane is known as phase space, right. Okay. So, basically the state of a system at any given point is decided by two independent variables. One is the momentum of the particle and other is the position of the particles, right. So, okay. So, now like I said, we can divide this phase space, this plane into infinite number of points, right. But since we do not really want our entropy to diverge, omega to be finite, so we have to, there must be a way where we need to discretize this phase space, right. So, how do we discretize it? So, discretization of phase space. All right. So, remember, like I said, say we just consider one point. So, our r coordinate can be associated with an x, y, and z, x, y and z. Similarly, p coordinate has px, py and pz components, right. So, for simplicity, let us stay in the x and px space for the time being, right. So, this is x and this is px, okay. But you should remember that for a 3-dimensional real space, the phase space is a 6-dimensional space, right. So, for one particle, one molecule or particle, one molecule, a 3D real space corresponds to 6-dimensional phase space, okay. So, at any given point a molecule in the system has certain x position and certain x component of the momentum, alright. Alright. So, basically but and in order to find the microstate of the system, we need to know its position and momentum at the same time. But you know, there is a very fundamental principle in quantum mechanics which is known as uncertainty principle. So, which is as follows, right. So, due to uncertainty principle, so due to Heisenberg's uncertainty principle, we cannot really measure the position and momentum of the particle with utmost accuracy, right. So, the error with which we can measure the position of a particle, which is delta x, and the certainty in which we can measure the momentum of the particle, which is delta px, that is always greater than or equal to h divided by 2 pi, and h divided by 2 pi is also sometimes denoted as h cross, alright, and this is the well known Planck's constant, right. So, therefore, what I am saying is, we, based upon this fact, we can now discretize our phase space, right. So, we can like draw these lines, right, and we can discretize this phase space into these squares such that so this area of this particular square, okay, so which corresponds to delta x here and delta px x here, and the area becomes h, right. So, this is how we can discretize the phase space, right. So, at any given point, the accuracy with which we can measure the position and momentum and product of these two has to be greater than h. So, therefore, there cannot be infinite number of microstates as we were earlier afraid of, essentially, right, earlier worried about, alright. And this Planck's constant is a very tiny amount, right. So, it is discretized, but it is ever so slightly discretized, right. So, if I mention the value of Planck's constant, it is 6.63 into 10 raised to the power minus 34 in SI units, which is meter square kilogram per second, right. So, it is a very small value, but still a finite value, not a zero number, right. So, therefore, this helps us to get a finite number of microstates, albeit they can be as large, that can be a very large number, but it is still a finite number, alright. So, the way we have discretized the x and px plane, similarly we can also discretize the y and py plane and z and pz plane, right. So, similarly, so delta y times delta py is also greater than or equal to h cross delta z times delta pz is also greater than or equal to h cross, right. So, therefore, in a 3D space, in a 3-dimensional real space, which is equivalent to 6-dimensional phase space. So, the volume element, right. So, in 6D phase space, the volume of discretized space, the minimum volume is basically h, which is delta x, sorry, which is delta x delta px times delta y delta py times delta z delta pz, and this is equal to, or actually greater than or equal to h cross cube, right. So therefore, at any given point, so say I prepare a system where the momentum varies from 0 to p, or so 0 to p and position coordinate goes from 0 to r. So we have some finite phase space volume. So we can divide this volume by the volume of this single discretized volume element, and then we can get the total number of microstates, right. So therefore, total number of discrete microstates in a problem, in a system, is basically total phase space volume divided by this quantity h cube, right. So I am just dropping the cross sign here, and this is divided by h cross. And like I said, as you already have seen, h is a very small number, right. If I take third power of it, it will go to about 10 raised to minus 100 or something, right. So this is a very large number, but finite, okay, all right. So this is how we can basically come out of that problem, that how do we make number of microstates in the system a finite quantity, all right. So just to get an estimate or idea what is this large number that we are dealing with, so let us do a very quick example. Let us take a quick example. So basically, so we are interested in, okay, so what is the or the ratio of number of microstates in 1 gram of water between two temperatures, right, between 300 Kelvin and 300.0001 Kelvin, right. So I have heated my water, 1 gram of water, by a very tiny amount, like 1/10 is like a fraction of 1 Kelvin, right. So I have just increased it to 300.0001 Kelvin, and the question that we are trying to ask is, as a virtue of increasing this temperature, how many additional number of microstates we have introduced into the system, the accessible microstates that we have introduced into the system. Okay. So for that it is fairly simple. So basically what we can do is we can calculate the change in entropy of water, of this 1 gram of water between 300 Kelvin and 300.0001 Kelvin, right. So basically change in entropy between 300 and 300.0001 Kelvin, right. So that would be delta S, and this is basically delta Q divided by the temperature, right. And what is delta Q? That is the mass of the water multiplied by the specific heat, right, specific heat, and multiplied by the difference between two temperatures, right. So final temperature minus initial temperature, and divided by the temperature at which this process is happening, which is very close to 300 Kelvin, right. So we are not really changing that too much. And as we know, we have used 1 gram of water. So this is 10 raised to the power minus 3 kilogram times the specific heat of water in SI units is 4185 joule per Kelvin per kilogram, right, and multiplied by Tf minus Ti, which is 10 raised to the power minus 4 Kelvin, and this quantity divided by 300 Kelvin. Okay. So this is what is the entropy change in the system as we raise the temperature of 1 gram of water by 0.0001 Kelvin, all right. And this quick calculation we can do, and we can find out that this is a number which is small, 10 raised to the minus 6 joule. So this is the change in entropy, all right. But now we can use the statistical definition of entropy, right. But from Boltzmann equation, equation of entropy. So, what is delta S, right? So, delta S is basically Kb log of final number of microstates after we have heated the water minus Kb times log of initial number of microstates, which is at 300 Kelvin, all right. So, and now we can basically plug in these numbers. So, this is 1.4 into 10 to the power minus 6 equals Kb log of omega final by omega initial, and we know Kb is a number which is 1.38 into 10 to the power minus 23, and right, and this is joule per Kelvin, right. So, therefore, we can see that log of omega f by omega I equals, okay, so this should be joule per Kelvin, sorry, so this should also be joule per Kelvin, all right. So, therefore, we can see that log of omega f by omega I comes out to be so 1.4 into 10 to the power minus 6 divided by 1.38 into 10 to the power minus 23, which is a number approximately equal to 10 to the power 17, right. So, which implies the number of microstates after we have heated the water by 0.0001 Kelvin divided by number of microstates at 300 Kelvin is essentially e raised to the power 10 raised to the power 17, right. And this is a humongous number, right, it is astronomical. I mean, it is even difficult to make sense of it, how big this number is, right. So, it is like saying, so there are 10 raised to the power 17 zeros after a number which is close to 3, right. So, it is one way to think about a number which has 17 zeros after 1, but here there are 10 raised to the power 17 zeros after 3, all right. So, this is a huge number, okay. So, now, and this is basically because the Planck's constant value is so tiny, all right. So, even though this number, which is the number of microstates accessible to a system, is a finite number, but it is still a huge number, right. And remember, initially I said the statistical physics works only if we have very large collection of particles which ensure that the number of microstates, the laws of probability that we are applying to a number is humongous, right. It is 10 e raised to the power 10 raised to the power 17, and this is just for tiny bit of water, 1 gram, whose temperature is raised just by 0.0001 Kelvin, right. But now you think about the real systems like this metal or this glass of water or oceans and atmosphere and so on. So, how accurate this theory would be, right. All right. So, the next thing that we will do is basically density of states. Right. So, we just saw that as we increase the temperature of any system, the number of accessible microstates increases basically faster, it is exponentially, like it increases really quickly, right. It goes to a very high number. But now we want to see how many microstates are there in a per unit energy interval, right. So, say I increase the energy of my system by a slight amount, how many accessible microstates are present in that energy window, all right. So, remember we saw that we can discretize our phase space, right, into a tiny volume element, okay. So, basically so we saw that so the number of discrete microstates in a small volume element dq bar dqp, and that number is basically equal to the volume of this element, right. So, what do I mean by dq bar, and maybe I can rewrite it in this way, right. So, in dx, dy, dz, dpx, dpy, dpz, right. So, this is this number is this is what now I am writing it as d cube of r and d cube of p, and divide this by the Planck's constant cube, right. So, this many number of microstates will be present in this small incremental volume element in a 6-dimensional phase space, right. And then okay, so this is the number of microstates present in this tiny volume element. Then what will be the total number of microstates present in any system, right. So, therefore, total number of microstates. So, total number of microstates basically will be an integral of this quantity, right. So, 6 integrals essentially. So, this will be 1, 2, 3, 4, 5, 6 d cube r d cube p divided by h cube, where each integral corresponds to the increment in the position space and the momentum space, right. And this integral basically goes from 0 to some r, right, like the spatial dimensions of the system, and 0 to p, which is the momentum in the dimension of the system in the momentum space, all right. So, and it is very obvious, like the triple integral of d cube r will basically give you the volume of an element. Say we are working with certain volume of the gas, right. So, it's triple integral in the real space will be the real volume of the gas that we have in front of us. But what about the momentum space, right. So, and since remember in kinetic theory we saw that the gas molecules, for example, they can point in every direction equally likely with all the magnitudes and so on. So, therefore, and there is a spherical symmetry, since there is no preferred direction in this problem, there is a natural spherical symmetry in the problem, and we can work in spherical polar coordinates, right. So, therefore, the volume element in p space in spherical polar coordinates that would essentially be d cube p, which is p squared sin theta d theta d phi and dp, right. And so, basically what we are doing is we have a sphere which is centered here, and we are basically dividing this space into. So, we are maybe I should do a better drawing. So, we are slicing it into a thin slice of thickness dp, right, dp, and this is at an azimuthal angle theta. So, sorry, the polar angle theta, and there is this complete ring which has an associated azimuthal angle which goes from 0 to 2 pi, right. So, therefore, so here the p increment goes from 0 to p, 0 to p. So, theta goes from 0 to pi and phi goes from 0 to 2 pi. So, which corresponds to moving along this thin ring which we have cut off from this spherical object which is in p space, right. And the thickness of this shell, essentially thickness of this shell is, sorry, okay. So, essentially what I am saying is, so thickness of this shell okay. So, this is dp, and there is an appropriate thickness which corresponds to certain component here, and most importantly the limits goes from 0 to p, 0 to pi and 0 to 2 pi, all right. So, therefore, what will be the total number of microstates, right, and that now we can denote as n of p, right, and that will be 1 divided by h cube. So, this h cube will come out, and there will be a triple integral corresponding to the position space. So, let me write it here. And there is first integral which goes from 0 to pi sin theta d theta 0 to 2 pi of d phi and 0 to p of p square dp. Okay. And now we can solve this integral. So, like I said, the triple integral in the position in the real space is basically the volume of the system, capital V divided by h cubed. So, this the integral of sin theta is minus cosine theta, and between 0 to pi this will become cos 0 minus cos pi, right, times d phi, which is times 2 pi times p square dp goes from 0 to p. Okay. And like I said, since we are interested in density of states as a function of energy, right, increments of energy. So, we need to convert our momentum into energy, right. So, therefore, what we can use is we can use the relation that energy is equal to p square by 2 m, which implies our 2 p dp will be 2 m e 2 m de, sorry, 2 m de, and that would give us p dp equals m de, and if I multiply both sides by p again, so my p square dp will be m times p, which is square root of 2 times m e, right. So, square root of 2 m e times d e. Okay. And we can now substitute this back here. Okay. So, therefore, we can now write our n, the number of number of microstates at any given energy E, that will be equal to V divided by h cube, and this will give you 2, right. So, cos 1 minus of minus 1 times 2. So, this will give you 2 pi times 2 pi, and I am rewriting this as so 2 raised, okay, so I am writing it as 2 raised to the power half times m raised to the power 3 by 2 and integral of E half dE, where now energy goes from 0 to E. Okay. And this can be little bit of algebra, you can simplify it to this expression. So, 4 square root of t times V times pi times m 3 by 2 divided by h cube, and this is 0 to E, E half dE. Okay. Okay. So, now we can define the density of states as follow, right. So, defining density of states. So, dE, which is basically the number of microstates integrated over a volume. So, the density integrated over a incremental energy will give me the total number of give me the density of states, right. So, therefore, if we compare these two expressions, so we can see that the density of states grows as, most importantly, it grows as e raised to the power half with some coefficients in front, which is 4 pi v times square root of 2 m raised to the power 3 half divided by h cube, right, and this is the density of states in 3D, right. So, in 3 spatial dimensions, all right. Okay. So, that is an important result. So, the next thing that we will do is basically statistical ensembles. Okay, statistical. So, like we mentioned before, right? So a typical microstate for n number of particles in a system, right? So, say I give you a system which has n number of molecules, right? Right. So, like I said, the microstate. So, typical microstate or a typical microstate corresponds to the individual position and momentum coordinates of all the gas molecules at any given point, right. So, basically and that system, since it is evolving as a function of time, so we can assign a function to it, right. So, so basically so basically the system will this microstate will be okay. So, basically at any given time, so the microstates will look like this. So, say there are 10 raised to the power 23 particles or molecules, let me use the word molecules. So, say there are 10 raised to the power 23 gas molecules or molecules in the system. So, the microstate will give us the information about the position coordinates of all the gas molecules at any point and all the momentum vectors at any given point, right. So, this can be written as x1 to xn, y1 to yn, z1 to zn. Similarly, px1 to pn, py1 to pn, pny, this is x, and p1z to pnz, right. So, this is what, so all these independent variables, which is 6 times 10 raised to the power 23, like 6n variables. So, 6n independent variables, right, and a function so a function which is a function of 6n independent variable that determines the trajectory of or the direction in which a particular thermodynamic process is evolving as a function of time, right. And you might already basically guess that this is a very difficult problem, right. So, it's very hard to keep track of all the gas molecules positions and momenta all at the same time, and this, and as we know that the underlying reality of any system is a chaotic, right. So, a molecule is undergoing collisions all the time, it is changing its position. So, there is so it's really impossible to predict the trajectory of any single molecule in a phase space, right. So, therefore, to really understand a system over as a function of time, we have to keep track of all these variables, right. But it turns out it is not really necessary, and there is an alternate way to handle such a problem, right. And that is where the concept of these statistical ensembles was introduced, right. So, basically Gibbs in 1878 introduced the concept of statistical ensembles. Okay. So, which is as follows, right. So, so an ensemble represents a large number of identical mental copies of the same system, right, uh, 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 with each copy, basically with each copy corresponding to a unique microstate, right. So, what I am saying is, so rather than really tracking the position and momenta of all the gas molecules as a function of time, what we can do is we can rather take an ensemble of that, right. So, basically I can take huge number of screenshots of the same system, right, and in every screenshot there will be slight change in parameters, right. For example, the position of one molecule might get interchanged with the other molecule, but the system will still be the same, right. So, for example, in this room, if I replace this molecule with this molecule and keeping everything else same, their speeds and their velocities constant, the system will still behave the same way. It is still a thermodynamically equilibrium system, right. So, essentially what we will do is we will basically take snapshots of all the possible values of x, y, z, px, py, pz of that particular system, right. And those humongous number of mental copies form an ensemble. Okay. So, that is the meaning of ensemble. All right. So, to give you another simple example, so if I, for example, ask you a question, so if you toss a coin 1000 times, how many times you will get a head and how many times you will get a tail, right. So, you can see that there are actually two ways to answer that problem. So, you can either take one coin and toss it 1000 times, and you will, for example, most likely event is that you will get 500 heads and 500 tails. Okay. But there is another clever way of doing the same thing, right. So, I can collect 1000 coins and toss them all at the same time, right, and we will see that when they fall down, again the result will be same, right. So, there will be, statistically speaking, there will be 500 heads and 500 coins, right. So, what we have done is we have replaced the single the studying single system over a very long time, like tossing it 1000 times. We have just taken an ensemble of that system, right. So, we have just simulated it with 1000 coins all tossed at the same time, right. Similarly, if we want to, for example, say we want to learn about how the star ages, right. So, say there is a star formation in the sky. So, it forms, then it like undergoes all the changes and it dies. So, either we can just track a single star over its entire lifetime, which is impossible, right. So, what we can do is we can like observe trillions of stars all at the same time, which will obviously form an ensemble of the same system, and we can make predictions out of that, right. So, this is how this is where this concept is really based. Okay. All right. So, basically what I just said is also known as what is known as ergodic hypothesis. Which basically means that for a physical quantity, x, right. So, for example, okay, so say I give you a system and you want to measure certain physical quantity which is x, right. Maybe it is pressure or temperature or something, or even in coin tossing it can be what is the what is the total number of heads, right. So, that is a physical quantity. So, either you can toss a single coin 1000 times, or you can work with 1000 coins and toss them all at the same time. You should get the same answer, and that is essentially the ergodic hypothesis, which means the average of this quantity x measured as a function of time, right. If you just work with signal system, that is equal to its average performed over the entire ensemble. Okay. So, this is the ensemble average and this is the time average, and ergodic hypothesis says that both are equal, right. So, you do not really have to track the system over time for a very long time. You can just do an ensemble average and get the same result. All right. And based upon how we design a thermodynamic system, we can basically work with various ensembles, right. So, there are various ensembles corresponding to that. All right. So, there is first known as microcanonical ensemble. Okay, so there is micro canonical ensemble, canonical ensemble, grand canonical, and so on. Okay. And in a micro canonical ensemble, all the molecules have all the ensembles copies have same number of particles, same volume and same energy. Similarly, in a canonical ensemble, all the systems, all the ensemble copies have same number of molecules, same volume and same temperature. And similarly, in a grand canonical ensemble, we have same volume, same temperature, but same chemical potential. Okay. So, let us see how we can visualize this, right. So, in order to have a conserved number of particles, the system must be closed, right. So, all these particles, they must be always inside the system. In order to fix the volume, the wall should be rigid, there should not be any movement of the wall, and to preserve the energy we have insulate this system, right. So, we should so this system should not really exchange heat with its surroundings, right. So, if we do that, so the number of particles, the volume and energy will remain conserved, and this is known as a micro canonical ensemble. Okay. So, and we can develop multiple copies of this system which have same number of particles, same volume and same energy, but the positions and momenta all can be different between different mental copies, depending upon all whether that particular microstate is accessible, right. Okay. So, similarly, we can draw the canonical ensemble as well, where you have again you have rigid walls. You have closed system where the number of particles does not change, you have rigid wall so that the volume does not change, but now the system can exchange heat with surroundings, and say it is in contact with certain reservoir, so its temperature remains constant, and this is a canonical ensemble. Okay. And now similarly we can have grand canonical ensemble where system is now open, right. So, the number of particles is not fixed, so particles can actually go out and in, but it has a certain chemical potential, a certain temperature and certain volume, right. So, say the walls are still rigid, it is still in contact with a huge reservoir which is at certain temperature T and a chemical potential mu, right. So, this is grand canonical ensemble. And basically now you can see that depending upon what are the parameters, natural variables in the problem, we can come up with many more ensembles. So, for example, another useful one is, which we have already actually discussed a little bit during phase transition, is isothermal isobaric ensemble. Okay. And basically here we are keeping the temperature and pressure constant, right. So, there is an external pressure, so this is in contact with the reservoir at temperature T, and such that, and this is a closed system, so particles are not really leaking out. So, you have fixed number of particle, fixed temperature and fixed pressure. Okay. So, this is a isothermal isobaric ensemble, and the last one which is known as isoenthalpic isobaric ensemble. Okay. So, since it is isoenthalpic, so we can now insulate this system, okay, and we can put the pressure P, okay, such that the number of particles is constant, the particles are not leaking out, the pressure is constant, and since pressure is constant, internal energy is constant, the pressure is constant. So, therefore, the enthalpy of this system will remain constant, right. So, H will remain constant, and this is a typical example, and this is how a typical isoenthalpic isobaric ensemble looks like. All right. So, in the next class we will now start going into the detailed understanding of microcanonical ensemble, and we will see how we can make connections to the thermodynamics. All right. So, see you in the next class. Thank you.